I will try not to be too technical and to introduce in this talk what I think is an important research program, a program that looks interesting to me. Okay, so I will start from describing the idea of online testing of statistical hypotheses. So essentially, it's using test martingales for testing. And then you can apply conformal prediction to this problem, to solving this problem. You can design conformal test martingales using conformal prediction. A natural question is if conformal test martingales have any serious limitations. So actually, when we introduced conformal test martingales already in our 2005 book, but at that time, I believed that conformal test martingales must have some limitations. But now I'm more optimistic about them, and here I will talk about some about a really simple special case. And in that special case, I will try to demonstrate that they're performing really well. The goal here is to design practically useful conformal test martingales. But in this talk, I will be mainly considering some very simple situation, and it will be just playing with this notion. But still, probably the ideas that you can come up with in this simple model situations, they can also be useful in practice. Okay, so let me start. So the introduction is a big part of this talk. So here there will be another talk on this topic by Alex Gamerman in the afternoon. And Ilya Nuridinov has a poster tomorrow on a similar topic, but his model situation will be more complex. It will be continuous. It will not be binary. Okay, so the idea of conformal testing. So conformal prediction, as many people mentioned it earlier today, so it outputs predictions that are provably valid, but they are valid only under the ID assumption. So in conformal testing, we just turn this idea on its head. So suppose our predictions are not valid when we are using conformal prediction. It means the ID assumption is wrong. So it's a way of testing the ID assumption. So how can we do it? So first, let me talk about online testing of statistical hypotheses. So of course, testing statistical hypotheses is a standard topic in statistics. But in statistics, people are usually interested in the batch setting. So we're given a fixed batch of data, and we want to decide if our null hypothesis should be rejected or not. We never accept it. So we can reject it, or maybe we don't have enough evidence against the null hypothesis and we don't reject it. But this is not what we need in machine learning, for example. Suppose we want to decide, so this will be the topic of Alex's talk, but one big application of testing the ID assumption is to decide when a prediction algorithm should be retrained. A naive approach would be to say you retrain it if its performance deteriorates, if its predictions cease to be good. But we don't have any threshold. Maybe this deterioration is just a statistical anomaly. And maybe actually the world became nicer to us. Maybe we can achieve a better performance, but we can miss it. So it would be good to have some rigorous ways of testing the ID assumption. For example, for this purpose of deciding when to retrain. Okay, so in online testing, instead of testing a batch of data, the data is arriving all the time in a stream. So it's similar to what Shen Shang was talking yesterday in his invited talk. So here we continuously monitor our incoming data for deviations from exchangeability or deviations from the ID assumption. The way we can do it is to use test martingale. So what is a test martingale? It's a way of gambling against the null hypothesis. So it's some process, it is a discrete time process, S0, S1, and so on. We start from 1 pound, S0 is 1, and the process is fair. The expected value of Sn is the previous value. So on average, we don't lose, we don't gain under the null hypothesis. And it should be non-negative. No debt is allowed. We should use only our available capital of 1, the initial capital. Okay, so we are gambling against our null hypothesis. So if the null hypothesis is correct, we don't expect to gain a lot. But if it's wrong, of course, everything is possible. And if our capital becomes very, very large, it means we are entitled to reject our null hypothesis. Okay, so here our ID model, our null hypothesis is the ID model, the only statistical hypothesis considered in the mainstream machine learning. So it's huge. So we are talking about non-parametric statistics, and there are no ways of testing this hypothesis in statistics unless your observations are real numbers. But it's my next slide. But let me tell you what I'm going to do here. So the goal here is to design conformal test martingales. Martingales valued under the ID assumption. And they're constructed based on conformal prediction. So I will tell you how this can be done. Okay, let me see. Yes, so here, so it's in statistics, you can test such big hypotheses even in non-parametric statistics. You can do it in the batch mode, and if your observations are real numbers. But of course, in machine learning, we are interested in pairs, x, y. Y can be a real number when we are talking about regression, but we also have an x, and x can be huge. And you would like to have methods that are applicable in this general situation when we have pairs x, y. But I will consider a model situation where y is binary. It's either 0 or 1, just to see if conformal test martingales have any limitations. It's a very specific way of testing the assumption, the ID assumption. But let's try and see if there are any real limitations. Okay, so this paper and this talk is inspired by this paper by Aditya Ramdas and et al. About testing exchangeability. So in their paper, they consider the binary case. And they introduce a process Rn, which is it's essentially, it's not quite a test martingale, but it's almost a test martingale under the ID assumption. But their method works only in the case when we have finitely many possible observations. So best of all, it's our observation space should be binary. So for binary observations, they can introduce this process Rn, but it doesn't generalize. Conformal test martingales, what is good about them, they generalize at once. So in this problem, you can also apply a conformal test martingale, which we called simple jumper. It was already, in our book, we had a more sophisticated version, sleepy jumper. But this element of sleeping, it's not needed, and you can improve results. So in recent papers, we showed that you can improve the results in our book by discarding this element, simplifying our test martingale. So we just applied the standard test martingale we used in previous papers. So each of these martingales becomes astronomically rich when gambling against the idea assumption in the model situation considered in this paper. The same model situation will be considered in this talk. I will describe it in a minute. So what they can achieve something like 10 to the 20. So it's important that Rn it's designed not for this model situation. It's designed for some Markov alternatives. But they decided just apply this process outside the domain for which it was designed. And they still got this excellent result, 10 to the 20. So they can make 1 into 10 to the 20, it means it should be rejected. And these astronomical numbers, so I'm interested in them only to compare different approaches. In practice, of course, 10 to the 20 is more than enough. We can reject our hypothesis. But in this case, I just wanted to consider this model situation and find out how rich we can become. So this is what's simple. The line in blue, what the simple jumper can gives you. So it's like 10 to the 90. It's much, much better than this process, R to the N. Sorry, Rn. Can you get even more? So what's the limit that can be achieved by conformal test martingales, and is it any good? So here, let me describe this model situation first. So the research program is to consider all kinds of model situations and see if conformal test martingales perform well, if they can reject the idea assumption when it ceases to be true. Okay, so here I consider, so the observations are generated by Bernoulli distributions on my observation space 0, 1. And pi is the probability of 1. It's the only parameter. So my null hypothesis, pi is the same all the time. And my true distribution, my model situation, is when there is a change point. I have 10 to the 4 observations overall. The first half, the first 5,000 are generated from this distribution. The probability of 1 is 0.1. But then at observation 5,000, it suddenly changes. It's an easy change. It's a drastic change, and it's easy to detect. So it changes to 0.4. So this is my model situation, 5,000 from 0.1, and then 5,000 from 0.4. And let's see how rich we can become. Okay, so as I told you, I already mentioned Rn works only for essentially binary observations. But conformal test martingales, they're very, very specific. I will define them in a minute. So my main question, if this method imposes any limitations, maybe it's a straitjacket that is imposed on us and we can't detect exchangeability, lack of exchangeability properly. So now let me tell you the idea of conformal test martingales. So if the observations are coming sequentially one by one, we can compute p-values. So it's important our p-values should be randomized. So we have this random number theta n for breaking ties, but conceptually it's very important. So in practice, if n is big, it doesn't affect your p-value much in many cases. Not in this case. For the binary observation, it's important even when n is big, because our observation space is so poor. But in normal applications, it doesn't matter much in practice, but it matters a lot conceptually in theory. So now we know that Pn are distributed independently and uniformly. And now this is what we can test. So we transform our huge null hypothesis, the ideal null hypothesis, we transform it into a simple hypothesis. Now we are testing if Pn are really uniformly and independently distributed, which is easy to do. It's a simple hypothesis. Okay, so here, the way we express it, how we express betting is we talk about betting functions. So a betting function is a function f, which maps 0, 1. So which maps a p-value into some number, f of p. And this will be the increase in our capital. Our current capital will be multiplied by f of p. So in order to make this process fair, the game should be fair. So we multiply it by f of p. F is non-negative. It can be infinite, by the way. But here it's not very important in practice. So in order for it to be fair, the integral of f should be equal to 1. It's the only restriction. If it's true, we can use these betting functions. So the idea is that at step n, we choose a betting function fn, which can depend on the previous p-values. So this way we are gambling against the non-uniformity of p values. Okay, so this is our idea. And now the product, what you get is the product of these the values of these betting functions. So Sn is our conformal test martingale. So it's a very, very easy and natural definition. This is how they're defined. But maybe there are lots of other ways of testing the idea assumption. It's one specific way. How good is it? Okay, so let's try and check it. So we know that the simple jumper, for example, it attains huge final values, but still we don't have any benchmark. We don't know how good it is, what is attainable. So first, what we can do, so we can design an ideal test martingale for this model situation. I will not go into the details. I wrote here an explicit expression for the ideal betting function, but the idea is that it's known from our previous paper by Valentina Fedorova et al. It's known that the best, in some sense, the optimal way of gambling is to use the true probability distribution function of the p-values. So if the p-values are uniform, as they should be under the null hypothesis, the optimal function is just identical one. You don't gamble at all. But if you know it's not uniform, you can gamble. And the best function is to use the true PDF. And in this model situation, it's very easy to compute the true PDF. Okay, so we can do this, and we can use it as our, sorry, I didn't, so to define a conformal predictor or this conformal test martingale, we need the nonconformity measure. But we just take the trivial nonconformity measure. The nonconformity measure of y is equal to y. You are surprised at once, and you are not surprised at zeros. Okay, so this is our, this works well enough. You don't need anything better. But now you can use this optimal betting function. And this is what you get. What you get is, so I call it custom-made conformal martingale. So it uses it uses the full knowledge of our true distribution. So it's shown in black here. So we can see it achieves like 10 to the, like, it looks like 255. So this value is the best you can achieve using conformal martingales. It might not be quite the best, because there were some approximations on the previous slide. But this is what you can achieve using conformal martingales. But now we need some benchmark. So one possible benchmark, I call it lower benchmark. So it's shown here in green. So this is the best. So my interpretation of it is it's the best you can achieve without any restrictions, without restricting yourself to conformal test martingales. And in the binary case, it's feasible to have this quantity. So the idea is that, so let me tell you how this lower benchmark is defined. I think I have enough time for that. So suppose you know suppose our null hypothesis is simple. You know this, the true probability of one, you know pi, the true value of pi. Then the optimal test martingale is the likelihood ratio of the true distribution divided by the null distribution. But now you don't know pi. So you just take the minimum of these likelihood ratios over pi. Okay, so this is a lower benchmark. So unfortunately, it works only for some very poor observation spaces. In the paper, I also introduced the upper benchmark. It works for any null hypothesis, but lower and upper benchmarks, they're really, really close. So let me show you. Okay, so there is an element of randomness here.
You have
so these
minutes.
are.
Yeah, you have 4 minutes. Yeah.
Okay. These are box plots for lower benchmark, for upper benchmark. They're base 10 logs, and you can see they're extremely close. It doesn't matter which one you choose. You can ignore this one. It's for some pseudo martingales, and for conformal martingales you get this. So the median is 270, and this ideal median is like 275. So you can improve, maybe you can improve the performance of this conformal martingale, but it approaches the benchmarks closely. But the next question is, why do we need it? It seems we have, it looks like cheating, because this conformal test martingale knows the true distribution. But you can look at the formula for this optimal martingale closely, and you can get some ideas. You can see what you get it from your mathematics. You have some optimization problem, but then you can try and understand what it's doing. And then you can simplify it radically. So 2 ways of simplifying it: sleeper stayer. It's a very, very primitive conformal test martingale. It doesn't have, it's even simpler than the simple jumper. And it performs well because it's modeled on this optimal martingale. And then you can use sleeper drifter, which is optimized very, very slightly. It doesn't use, for example, the knowledge of where the change point is, 5,000. It doesn't use much information at all. It's something that can work well outside this simple model situation. And you can see they perform, so this is a simple jumper, they perform much, much better. So here's the idea is that you fix a model situation, and then you get some ideas for practically useful conformal test martingales. Okay, so these are directions of further research I think are useful. So yes, of course, I mentioned we want natural conformal test martingales, and you can get lots of ideas from the form of these optimal ones. Then, of course, we should try and do something similar in non-binary situation, ideally for observations which are pairs, x, y. And we can consider other alternative hypotheses, like Markov instead of a change point. So let me give you some references. So references our ICML 2012 paper, Fedorova et al. So here we just show that the optimal betting function is the PDF of the p-value. It's a very, very simple result, but it's stated there clearly. So I have a theoretical result about the optimality of conformal test martingales in the binary case as well. So it's a paper. It's been published as an archive report. And also tomorrow, Ilya will be talking about another model, another set of model situations, which are continuous model situations. So he will do it in tomorrow's post. Okay, thank you. That's all from my talk.
Yeah.